Okay, guys, section 1.4, first video. Hopefully you read the section. You know, you are supposed to read the sections along with watching the videos, okay? So the first video on 1.4 here, you may have noticed that they told us that I is equal to the square root of -1 and I squared, if we squared both sides, is equal to -1, which makes sense. If I were to square both sides, you can see you get right here, okay? So why the heck do we care about this? And they also said something about standard form. You may have seen this, a plus bi, where a is the real part and b is the imaginary part. Well, what are they talking about? Well, back, I'm not sure the year, but they were trying to solve different types of equations, right, as they were developing math. And eventually they got to an equation that may have looked something like this, x squared plus 25 equals 0. Seemingly very easy. And as you know, one technique you can use is you can get the x squared by itself and move the other term when you don't have that middle x term. And normally from here to undo a square, you take a square root. You usually have to do a plus or minus. So if you did take a square root, you would get something like this. Well, what does that mean? How do you do the square root of -25? Remember, square root asks what times itself is equal to the thing under the square root. Well, there is nothing times itself that equals -25. So they ran into problems when they were trying to solve equations like this. The other strategy to try to factor this, that's not going to work either. That's a sum of squares. If you remember, that does not factor. So that's where they introduced I. And you might be saying, well, why do we care about I? It's imaginary anyways. Well, it actually has a lot of different uses in electrical engineering. Okay, so when you solve this, a lot of times you may convert it to imaginary numbers, and a lot of times you'll end up converting it back to real numbers, and it actually works out. The math works out just fine. Okay, so if we use our definition, what we end up with here, you have to remember your rules of radicals, is you could write it like this: the square root of 25 times the square root of -1. Okay, if you don't know how I did that, make sure you ask. Make sure you find out. You need to know that. And of course, we see this is plus or minus 5, square root of -1. By definition, we're saying it's I. So we have two answers here. Okay, this is two answers. It's -5i and +5i. Remember, I'm just writing this as a solution set. Okay, so the first thing we have to know how to do with these things is basic operations. And the way I like to do this is treat I just like a variable, just like an x. And the only other extra thing you have to remember is if you have I squared, you want to go ahead and convert it back to a real number. Other than that, it's the exact same thing you did in your previous algebra classes. So for example here, I'm going to treat the i's just like they're an x. Minus -9 would be +9 and plus 11i. Right? That's just distributing the negative. This is nothing new. Okay, there's no I squareds, but I can combine like terms. -7 and +9 is 2. 5i and 11i is 16i. And there's my answer in standard form. Very simple. My real part is 2. My imaginary part is 16. Okay, so that was just subtracting. Adding works the same way. Let's look at number 14 in the book now. Now this is a little different because they have multiplication. We're multiplying binomials. Well, I can do that with FOIL and it works the same way. So my first term is -24, right? 8 times -3. My outer, 8 times 9i, is plus 72i. My inner, negative times a negative is a positive. I have 12i. And finally, I have a -4i and a positive 9i. That's negative 36i squared. Okay? I can combine like terms. And I also want to keep in mind that I squared is -1. So let me rewrite it in that way. I have -24. Altogether, I have 84 i's, if I combine them as like terms. And finally, here I have -36 times I squared is -1. So really, I guess minus a negative, I guess that's plus 36 here. So I put my like terms together, I end up with 12 plus 84i. Real part is 12, imaginary part is 84. Lastly, I want to show you how division works with imaginary numbers. Now, to write our answer in standard form, because we want to divide this right in standard form, we can't have a denominator here. So what we're going to use is we're going to use something called the complex conjugate to eliminate the fraction. Yes, you can do this with an expression. Well, how do you do that? You do it the same way you would add fractions if it was just an expression. If you recall, right, if you had 1/2 plus 1/3, so really think back here, then the way you would add those is you would find the LCD, which is 6, and you can multiply the 1/2 by 3/3 and the 1/3 by 2/2. Hopefully this rings a bell. You get your common denominators and you got 5/6. We're going to use the same strategy as we did with the 3/3 and the 2/2 here. Okay? So over here, well, what are we going to use? We're going to use something called the complex conjugate. And I can do it as long as I do it to the top and bottom, right? Because if I multiply 1/3 by 2/2, I'm really just multiplying it by 1. I'm not changing it. So here, I'm going to multiply the top and bottom by what we call the complex conjugate. It's always the same as what I have here. We just flip the sign. Well, why? Okay, well, let's do it. Okay, here I distribute. This is a FOIL on bottom. On top, I get 12 minus 3i. On bottom, I get 16 from the first. Now, the outer is negative 4i. The inner is positive 4i. The i's have gone away. And then positive I, negative I, that's minus I squared. But keep in mind, I squared is -1. So what do I get? I get 12 minus 3i over, this would be 16 minus -1, or 17. What good has that done? Well, look, you can split the numerator. And usually I like to write the I out front. That way you can easily identify the real part is 12/17, and the imaginary part is 3/17. That does it for the first video.